Hello, my physics brethren. I think this is part 4 of chapter 12. Balance and stability. Stability depends on the position of the center of mass. Alright, the torque due to gravity will bring the car back down as long as the center of mass is above the base of support. So here's the base of support, and it seems to me that as long as this center of mass is to the right of this pivot point, it's going to bring it back down, but if it ever crosses it, then it's going to roll. Alright. This dancer balances in point by having her center of mass directly over her toes, her base support. I don't think I can do that. So more power to her. Which object is in static equilibrium? This seems like a review. Maybe there's a reason for that. I'm going to go with D. The reason I'm going to go with D is because C looks like a pretty good answer too. But there could be a torque here happening. Let's see. Let me think if the torque could happen here. Yeah, so for C, I think if you put a pivot point here in the middle of it, then I think you're going to get something spinning counterclockwise right here. This would want, yeah, so I think D is the right answer. Yep. All right, what does the scale read? Let's look at this problem here. All right, this is an interesting question. Think of the torque situation here. Here's the pivot point. Scale, since it has half the radius that weight does, it's going to have to push up twice the force. So to make it be in static equilibrium. So I'm going to say 2,000. But here's another way to think about it. If these things are balancing on that scale, like not turning on the scale, then if this is pulling down with 1,000 newtons, then this also has to be pulling down with 1,000 newtons, which again makes the scale register the full 2,000. That is correct. Rolling without slipping. What an interesting problem this is. Rolling is a combination of rotation and translation. For an object, I'm thinking this right here is a really good thing to know. The velocity, the straight line velocity of that center of mass right there, of this wheel, is equal to omega r for the point on the rim. And I really think it's interesting to think about the path that point on the rim follows as that thing rolls smoothly. Let me see if I can make this slide make sense. So they're talking about the velocity of any particle on this wheel. And they're saying that you can calculate that according to relative velocity kind of stuff. So if you try to recall what that is. So I remember it like this. If I say the velocity of A with respect to B is equal to, relative to B, A relative to B is equal to the velocity of A relative to C plus the velocity of C relative to B. So you just got to put a third object between them. And so I think the object they're putting between them is the center of mass. So what we can say is that the velocity of some particle I relative to just anything, let's say the Earth, is equal to the velocity of I relative to the center of mass plus the velocity of the center of mass relative to the Earth, which is kind of what this is saying, like this is this and this is this and this is this. So that's that, And that's that. Alright, so the velocity of the particle is the velocity of the center of mass of the whole object plus the velocity of the particle relative to the center of mass. The figure below shows how the velocity vectors at the top, center, and bottom of a rolling wheel are found. The velocity of the top is equal to 2 times the velocity of the center of mass, and the velocity of the bottom is always 0. The point on the bottom of a rolling object is instantaneously at rest. Alright, so let's see if we can... Okay, so this can make sense to us. This is a picture of translation, where nothing's rolling, everything's just moving at a constant velocity that way, everything at the same time. It's just sliding that way. This is a picture of rotation. So nothing is sliding at all, nothing is moving forward, it's just rotating, spinning a wheel in place. So when that's the case, you have this going at this velocity and this going at that velocity. So the bottom of the wheel is going that way, going to the left, and the top of the wheel is going to the right. But you add the two things together to get the situation with rolling. So you add these two things. So the velocity here plus the velocity here, that means that the top particle is going to be moving with twice the velocity of the center of mass, which is r omega. And that velocity of the center of mass is what it is because it adds with 0. The velocity at the bottom, they cancel out, so that's going to be 0. A wheel rolls without slipping. Which is the correct velocity vector for point P on the wheel? Ooh, I bet that's going to trick you. If it was not rolling, if it was just spinning in place, the velocity vector would be A. But because it is moving with, I think it's going to be moving with this velocity and this velocity at the same time, I think the overall velocity is going to be something like that. I think it's going to be C. And it is. Alright. Kinetic energy of a rolling object is, wow, 1/2 I omega squared. We already knew that. Plus, so if it's rolling, you have a rotational kinetic energy, but you also have a linear kinetic energy at the same time because both of them are happening. So you gotta add both of those guys. In other words, the rolling motion of a rigid body can be described as a translation of the center of mass plus a rotation about the center of mass with kinetic energy K rotational. So K rolling is a combination of those two things. We are getting closer to the end. One-dimensional motion uses a scalar velocity v and force F. A more general understanding of motion requires vectors v and vectors F. Similarly, a more general description of rotational motion requires us to replace the scalars omega and tau with those as vectors. Doing so will lead us to the concept of angular momentum. So we're going on to angular momentum now. The magnitude of the angular velocity omega is just the magnitude of omega, which is just that. The angular velocity vector points along the axis of rotation in the direction given by the right-hand rule as illustrated. Okay, this is important to think about here. Using your right hand, curl your fingers in the direction of motion with your thumb along the rotation axis. All right, so put your thumb in the same direction as the axis going through the wheel or whatever's rotating. Then you have to use your right hand. If you don't use your right hand, this does not work. That's why it's called the right hand rule. Then you have to be able to curl your fingers in the same direction as the rotation itself. So in this case, this way. And the direction your thumb points is the direction of omega. Now, let's say if this thing was pointing, let's say if this thing was rotating not this way, let's say if it was rotating the other way, let's say it was rotating this way. How would you have to orient this hand in order to be able to accomplish that. It would have to point down. The thumb, let me see if I can draw this. The thumb would be pointing down, and the fingers would be curling this way in order for this to happen. I know that's a terrible drawing. But then omega would be pointing down, so that would be a negative omega. So notice this, the original one is counterclockwise, and the one I just drew is clockwise, and they point in the directions that we've been saying the whole time, positive and negative respectively. All right, the dot product is one way to multiply two vectors giving a scalar. A different way to multiply two vectors giving a vector is called the cross product. The vectors A and B have angle alpha between them. I wish they didn't use alpha. That's supposed to mean angular velocity. Angular acceleration. Their cross product is the vector A cross B, which is AB. That's the magnitude of A, magnitude of B times the sine of alpha. All right, so A cross B is the magnitude of them times the sine of the angle between them. I guess it's when they're placed tail to tail. And the cross product is always perpendicular to the plane, so it's pointing in the direction that you get when you do that cross product there. The cross product is perpendicular to the plane of A and B. The right-hand rule for the direction comes in several forms. Try them all to see which works best for you. By the way, this also works for righty-tighty and lefty-loosey. If you orient your, for a screw, orient your thumb along the direction of rotation. So like this, your thumb. And then if it's curling to the right, if you curl your fingers to the right, your thumb's going to have to point down, which is why the screw is going to go in. But if it's rotating lefty-loosey, to make your fingers curl that way, your thumb's going to have to point up, that's going to correspond to the screw coming out. It's really interesting that they designed screws that way to abide by the right-hand rule. Note that B cross A does not equal A cross B. So there's A, there's B. That's another way to do the right-hand rule. You could put your thumb in the direction of one of the vectors, put your index finger in the direction of the other vector, and then do your middle finger perpendicular to your pointer finger, and it will have to point in the direction of the cross product. But that's the same thing. That accomplishes the same thing we said earlier. You put your thumb along the rotation axis and curl your fingers along the same direction of the rotation, and your thumb will point in the direction of the cross product. Have you guys ever heard of I think it's called a gyroscope? Maybe. I need to show you a video. All right, here's a gyroscope video.
From the channel Veritasium, and I've been following this series by Destin on Smarter every day about helicopters, and gyroscopic precession is just one of those things that still blows my mind as it did Destin's. So I'm here at the University of Sydney, my old stomping grounds. I'm going to borrow some of their lecture dem equipment to hopefully teach you a bit about how gyroscopic precession works. The first thing I need to do is talk about vectors, because a lot of things in physics are vectors. That means they have direction. So an example would be momentum and force. Those are two examples of some pretty common vectors. So if I have a cart moving along here, it has some momentum in that direction, and if I apply a force to it, I can change its momentum. So for example, if I push it to the right, then its momentum will increase to the right. It all makes a lot of sense. Well, there's a similar statement we could make about rotating bodies, which is that a torque increases the angular momentum of an object in the direction of that torque. So let's try to figure out those terms. If I apply a force down on this side of the wheel, I create a torque. Now, torque is force times the distance from the rotating axis. You could call it R. So torque is the force applied times the radius away from the turning axis. Now, what's the direction of that torque? Well, we actually use a right-hand rule to define this. And so what you do is you put your fingers in the direction of the radius from the turning axis and curl them in the direction of the force, and your thumb points in the direction of the torque. So the torque is actually out this way at 90 degrees to the force. The force is down that way. but the torque vector is actually pointing out this way. So the angular momentum of this wheel is being increased in that direction. So the more I apply this torque, the more I increase the angular momentum of the wheel in the direction of the torque. So I'm making this wheel have a very large angular momentum out towards the camera, out towards you. Now before I go any further, let's have a look at this setup that I've got. I have a wheel here hanging from only one side by this rope. And so right now there's actually a torque on the whole system if I let go, because the weight of this wheel is pulling down, and that force is applied at this distance away from its pivoting point there. So if I let go, well, it does exactly what you'd expect. The wheel swings down this way. But I want to see that as an example of rotational motion. There's a torque which is pointing out this way, which is trying to increase the angular momentum of the system in that direction. Now, angular momentum in that direction requires that the whole system starts swinging anti-clockwise. And so that is what happens. But what happens if I only let go after I've already spun up the bicycle wheel? Well, in that case, the bicycle wheel would already have angular momentum this way, and so a torque pushing that way actually swings this angular momentum round that way. Okay, so let me try to get the wheel spinning and make it work. Come on. Oh, look at that. It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque, and torque is pushing that angular momentum vector around. Except not for long, because this appears to be a quite frictionful wheel. So check out Destin's other videos about helicopter physics, and then come check out my channel, Veritasium, where
Is that wild or what? That is wild to me. That truly blows my mind. I don't understand it. I don't know that I ever will, but I certainly observe it and am amazed. How? Why? It just seems like magic. I just don't. You need to, if you could ever get your hands on a gyroscope, you need to do it and play with it and feel how that feels. I'm going to stop talking. I don't have any words to say that would do justice. All right. Hope I recorded that. Okay, yes, I have been recording. That's good. All right. Example: calculating a cross product figure that shows vector C and D in the plane of the page. What is the cross product of C and D, which we're going to call E vector? Alrighty. We're going to say, let's make this. We're going to say it's 1 times 2 times the sine of that angle between them, which is 110. And I think it looks like it's just that. Well, that is the magnitude of E, but the direction of E is given by the right-hand rule, which means you have to, let me think about this. I think the way you're going to have to do this, okay, this is how I was taught. You point your thumb in the direction of either C or D, then have your hand kind of open, then point your other fingers in the direction of the other vector. Like right now, I've got my thumb pointed in the direction of D. I've got my hand pointed in the direction of C. The rest of my fingers, that is. Now curl your fingers up, and they will point in the direction of the cross product vector. So they would point out of the page in this case. Let's make sure. Well, that says into the page. How in the world? Let me think about this. Here's why I was so mistaken. I just figured it out. I paused it and figured it out. It matters about the order. It's C cross D, not D cross C. So that means your thumb has to point in the direction of the first one. Your fingers need to point in the direction of the second one. So I'm going to point my thumb in the direction of C. I'm going to point my other fingers in the direction of D. And to do that, now I have to orient my hand so that when I curl my fingers, it now points into the page. All right. the torque vector. We earlier defined torque as RF sine phi. R and F are the magnitudes of vectors, so that this is a really, I think that's A's not supposed to be there. So that this is really a cross product. Alrighty, so when you exert here's a big old torque wrench on a great big bolt holding this wheel on. Okay, so it's R cross F. So here's R. That means we've got to put our thumb in the direction of R, put our fingers in the direction of F, and then curl your fingers out, and that will tell you the direction of the torque. When you do that, it's going to point out of the page, which this is lefty-loosey, and it's going to back that bolt out of there, out of the page. Particle of mass m is moving. The particle's momentum vector makes an angle beta with the position vector. All right, this is telling us that angular momentum is equal to linear momentum times the radius, but more detailed, to get that more precise, we do it as a vector. The angular momentum of a particle is equal to that particle's position vector, which we're going to say is an R vector, which is kind of like a radius, cross its momentum vector P. It's important we have that order the way it told us to, and that formula is on your formula sheet for your AP test. And to get the direction of it, you're going to have to put your thumb in the direction of the radius or the position vector, and your finger, the rest of your fingers, in the direction of the momentum vector, and then curl your fingers to tell the direction of this angular momentum. All right, so they define it here. L is defined as that thing we just said, which is also equal to, you know, if momentum here, P, is equal to mass times velocity, right? There's your M and your V, but it's written in a different order because M is just a constant. So I think that's why it's written first. So R times V are your vector, are the vector parts of this expression. Sine of beta, where beta is the angle between R and V, or the angle between R and P. So notice they put the two vectors together, tail to tail, before they were able to determine, using the right-hand rule, the direction of the angular momentum. Why this definition? If you take the time derivative of L and use the definition of the torque vector, see your book for details, you find that dl dt is equal to the net torque. Alrighty. Torque causes a particle's angular momentum to change. This is the rotational equivalent of dp dt equals F, and is a general statement of Newton's second law for rotation. Yeah, I remember that, because so if we write it this way, dp equals F dt, I remember it being like this, the integral, both sides, so P equals the integral of F with respect to time. That was, you know, that was J, right? That was impulse. Force times time. Okay, so yeah, so we can just put that into angular terms, and since L is the same thing as P but in angular terms, and tau is the same as force in angular terms, this all makes sense. For a rigid body, we can add the angular momenta of all particles forming the object. If the object rotates on a fixed axle or about an axis of symmetry, then it can be shown that all that stuff, L equals I omega, which is the same thing as P equals mv. So that makes good sense. All right, angular motion. Now we have this nice table again showing us the analogies between angular and linear motion, but with kinetic energy and and momentum and torque and all that stuff. An isolated system that experiences no net torque, thus the angular momentum vector is a constant. Law of conservation of angular momentum. The angular momentum L of an isolated system is conserved. Isolated system means there's no net torque on the system or outside torque or whatever. The final angular momentum is equal to the initial angular momentum, and both the magnitude and direction are unchanged. Conservation of angular momentum. As an ice skater spins, the external torque is small, so her angular momentum is almost constant. The external torque is small because there is very little friction between her ice skate blade and the ice. By drawing in her arms, the skater reduces her moment of inertia. This is what we talked about before. So when angular momentum is conserved, therefore the angular speed omega must increase. We've already talked about all this. Example. All right, that last example, here's the pertinent information for it. I believe we're conserving some momentum here. We're conserving angular momentum. Angular momentum L is equal to I omega. And so I for a disk is equal to something, and I for a loop is equal to something. Loop is a hollowed out disk. Let me see if I can go back to that good old slide where that tells me those things. There it is. All right, what are we talking about here? Cylinder or disc about the center, 1/2 mr squared. Cylindrical hoop about the center is just mr squared. Okay, I'm going to go with that. 1/2 mr squared and mr squared. 1/2 mr squared and just mr squared. So if we say that the initial momentum, and see, I think momentum is conserved here because if we consider this to be the system to be both disks, then the initial momentum is going to equal the final momentum. All right, the initial momentum is equal to the momentum of the disk initially plus the momentum of the loop initially. And the momentum of the disk initially is equal to 1/2 times the mass of that disk, which is 2, times the radius of that disk, which is 20 centimeters in diameter, so 10 centimeters in radius, so 0.1 squared, times the omega of that disk initially, which is 200 RPM. Oh gosh, I got to get that as a, you know what, as a radian. 200 revolutions. I have to do this like every time per minute. Maybe I'll learn a shortcut one day. 1 rev, 2 pi radians. 1 minute, 60 seconds. So let me pause it and calculate that. Okay, this is what I calculated for omega. So that's times 20.94. All right, that's this thing is the momentum of the disk initially, plus the momentum of the loop initially is 0. That's nice. So that's our initial momentum. What about our final momentum? Let me come over here. Our final momentum is equal to LDF plus LD, no, not LD, LLF. So the final momentum is equal to 1/2 times 2 times 0.1 squared omega, which is unknown. That's what I'm looking for. Plus, so this is LDF, plus the mass of that loop is 1. So I'm calculating that right now. So 1 is M. R again is 0.1 squared. And then omega for that is, again, they're going to have the same omega because eventually at the end of the day there, after the friction happens and their speeds catch up with each other, they're going to have the same omega. Good. This is great. I think we have ourselves a very good path to an answer. So we set all of that equal to all of that. That's going to give me 0.5 times 2 times 0.1 squared times 20.94 equals, I'm going to go ahead and factor out myself an omega times 0.5 times 2 times 0.1 squared plus 0.1 squared. So I'm just going to divide by all that and get myself an omega. I'm going to pause it and calculate it. Okay, I calculated omega to be 10.47 radians per second, the final omega. That makes a pretty good bit of sense, I reckon. It started out 20.94, ended up 10.47. It seemed like it's about exactly half, which I think is about right, because this thing is, it would have been just like if we had dropped a disc of the same exact disc on that thing. Because that loop, notice there's a 1/2 on the disc thing. There's not a 1/2 on the loop, so it's twice the I, but it's half the mass. So anyway, I think that's why it turns out to be half the angular velocity that it started with. Did that answer the question? Is that what it was looking for? Let me scroll down. Scroll some more. Here we are. What did it ask for? Final angular velocity. Yes, that's it. 10.47. Please be right. Shoot, it's giving it in RPM. Well, that means I got to convert it back. 10.47. No, it is 100 RPM because 200 RPM was twice that, 20.94. So 10.47 will definitely give me 100 RPM. I don't even have to calculate it. It's right. Good. All right. Quick check. 2 buckets spin around in a horizontal circle on frictionless bearings. Okay. Suddenly, it starts to rain. As a result, the buckets speed up. As a result, do the buckets speed up? Continue at a constant angular velocity. Slow down. Continue to rotate. Constant velocity. My gut tells me that's going to slow down because the mass out here is increasing, which is going to increase the moment of inertia. And to conserve the angular momentum, the angular velocity's got to go down to compensate for that. So I'm going to say C. And it's right. Advanced topic. Precession of a gyroscope. We kind of just watched the video on that, but this is worth looking at again. Consider a horizontal gyroscope with the disc spinning in a vertical plane that is supported at only one end of its axle as shown. You would expect it to simply fall over, but it doesn't. And that's what's so crazy. It's just magic. Instead, that axle remains horizontal, parallel to the ground, while the entire gyroscope slowly rotates in a horizontal plane. By the way, this is exactly why a top, when you spin it, doesn't fall down until it stops rotating. It's the same concept. It's the gyroscopic power. So let's see here. This steady change in the orientation of the rotation axis is called precession. We say that the gyroscope precesses about its point of support. The precession frequency omega is much less than the disk's rotation frequency omega. Oh, that's capital omega, that's lowercase omega. I'm going to let you guys read this. If you're interested in it, you can study it more because it did say it's an advanced topic. And I'd be glad for you to read some more about it. I'm sure the book has a lot about it too in that same section. But because we are so strapped for time, I'm going to not do that. Hopefully there won't be a homework question about it. If there is, I'll have to go back and look at it. But here is the example that it gives. You can read through these as an enrichment activity if you are so inclined and motivated. And we are to the summary slides. Hooray! And I'm not going to go through those either. We're done. That was the end of Chapter 12 videos. Hallelujah. Praise the Lord. And I hope that you guys are doing well on your homework problems. I'm going to put up a practice test as well. And we will work on those things on Friday. Get as much done as you can on your own. That way we'll have a very productive day together on Friday if you've already done as much as you can on your own. All right. See you next time.